Chapter 7, Lecture 4, Isentropic Processes of Ideal Gases. So we have an isentropic process of an ideal gas. There's two methods. One's what's called the approximate method, and then we have the exact method. The book goes through and develops these equations, and they're relations you may have seen in chemistry if you took. Sometimes they cover them in university chemistry. They may not have, but oftentimes they do. The book goes through and derives these equations. I'm not really going to do that. Uh, you know, so they're basically ratios. K can be looked up in a table, and we're looking at some examples in the problem. But the important thing here to remember for these equations is, first of all, they're approximations. Second of all, they're only for ideal gases. They're only for an isentropic process. Now remember what that is, when the entropy is constant. And they're also only this is only valid for constant specific heats. So that's the other case. Now, if you have there is a more exact analysis that we can use the tables on, which makes it obviously easier in a lot of respects. So when the constant specific heat assumption is not approximate or not valid, the isentropic relations developed previously yield results that are not quite accurate. So what the book does again is he goes through. So here's the basic equation. So if you set this to 0, you can solve this equation for the ratio of P2 over P1. This is where you get the exponential. And then we define exp S2 over R. We define that at what's known as the relative pressure. So you end up with this relationship here, which may look kind of odd. So you have P2 over P1, constant entropy, is a relative pressure divided by relative pressure. Now these relative pressures are in the tables, and I'll show you how to use that in a couple of examples. You can also do the same thing and get what's known as a relative specific volume. You can take the ideal gas law, solve for V2 over V1. You can end up with this ratio, T2 over P over P, the relative pressure. This is defined to be a relative specific volume. So you end up with this relationship here, and again, we'll go through this in a couple of example problems. So to get us started, let's look at example 710, isentropic compression of air in a car engine. Suppose air is compressed in a car engine from 22 degrees C at 95 kilopascals in a reversible adiabatic manner. If the compression ratio, V1 over V2, these are volumes. That's why he's trying to show you the odd looking font. These are big V's. So this is the volume ratio. So if the compression ratio is 8 for this engine, determine the final temperature of the air. So here shows the piston, it shows the initial state, it shows the volume ratio. So what this volume ratio is the piston moves up and down. The ratio between the piston being at the top of its stroke and the piston being at the bottom of its stroke is 8. This is 8 times compression. This is also shown in this TS diagram. Here you can see again that since this is isentropic, for the entropy, it's going to go from 1 to 2 on the straight up vertical, constant entropy. Entropy doesn't change here. But obviously the temperature is going to change, and the volume changes, of course. So if you look at table A17 for ideal properties of air, if you look at the temperature here at 295 Kelvin, it gives a lot of properties across here that we're familiar with. There's enthalpy. Look, here's the PR. This is the relative pressure. It gives the internal energy. And also, look, here's VR. So we can those values are right out of the tables, and of course, it gives the entropy as well. So for closed systems, the volume ratio and the specific volume are obviously related. They're proportional. So at T1 is 295 Kelvin, we can look up here, we can figure out the relative volume is 647.9. And then we can use that, the equation equation 750 in the book is the one on the previous slide. With the specific volumes is equal to the ratio of the volumes. So here, VR1, that's the 647.9 out of the table. The 1/8 is the ratio of V2 over V1. So when you calculate this, you get 80.99. So if you go back into the tables now, this shows more of the ideal gas tables. I only clipped a portion of this. I didn't put the whole table in here. But if you go into the tables and you look for a relative volume of 80.99, so you're over here in this column here, you look down through here, and so it's somewhere between here, right? Between 81.89 and 78.61. So we know the final temperature is going to be between 660 and 670, and of course we can interpolate and get the final temperature. T2 is 662.7 Kelvin. So if you want to convert this to Celsius, it's 367.7 degrees Celsius. You could have also done this using the approximate analysis, using the equations here as well. You could have done it a little bit harder, in my opinion. Although you don't have to go into the table, so maybe that might be easier in some situations. So K is the specific heat ratio, so you have to look that value up too, and you can find those values in table A2B. So if you look up that value for 450 Kelvin, it's 1.391. So you got you can solve this for T2. So T2 is T1, you got 8 is the ratio here, K minus 1, so you can calculate it here. But remember, this is an approximate analysis. It's more exact using the relative volumes and the relative pressures. In this case, you're only off by about 0.4%, as the book points out, which is kind of small, but the temperature change is not very large either, so that's why it was accurate in this specific case. Let's look at example 711. So here we have helium gas is compressed by an adiabatic compressor from an initial state of 14 psi, 510 Rankine, to a final temperature of 320 degrees Fahrenheit, which is 780 Rankines. We want to find the final exit pressure of the helium coming out here. And so again, this shows it on the TS diagram. The temperatures, initial temperatures is 510 Rankine, and it goes to 780 Rankines. Entropy is constant. So we're given the initial pressure. We're trying to find this final pressure here. So in this case, the specific heat ratio of K of helium is 1.667. And this is independent of the temperature in this region, since it behaves like an alkyl gas. So we can use that approximation here rather simply, solve it for P2, so 14 psi coming in, and ratio of temperatures, we get 40.5 psia.